So let me first, just for 5 minutes, repeat what, to summarize what we did on Tuesday. First of all, I tried to rewrite the notes a little bit. I got a lot of questions, so clearly it wasn't quite as clear as it could have been. So I updated the notes. And let me just try to summarize again what the whole point of the last lecture was. Okay, so what we talked about is there were really several topics in there. The first topic we talked about is a class of distributions that had a very specific form of densities, and these densities could be written in the following form. So these densities had some form like this. I can't remember if I used X or Y, but maybe I used Y, so let me stick with Y here. And so what were the parts in here? So h of y was just some non-negative function over the domain, and the domain could be just, let's say, the whole real line, or it could just be the integers, or 0 and 1. Then this phi of y, which was called the sufficient statistics, is in general a vector. So that's in general, in d-dimensional. And then accordingly, this parameter eta is then also now a vector in the same dimension. And the a was simply a normalization constant. And he made sure that if we integrated or summed over the whole input space, then this whole thing indeed gave us a probability or a density. And so these distributions, they're called, these are elements of what's called an exponential family. And we have seen that many distributions that we know, like Gaussian, Poisson, Bernoulli, but many, many other ones fall into this category. And so they themselves are nice, just to study themselves, because we saw that there were many nice properties. So for example, we saw that this was convex. We saw that the derivatives had some nice interpretation. So this was equal to the mean of this quantity under this distribution. Okay, maybe let me call it here eta. So that's this is under this distribution. P of eta, that was the mean. And we saw that the second order one was just the covariance. Okay, so that's the covariance of this vector here. Right, so these were just nice properties to have. And so because of that, they appear quite often. And so we did one application. I wrote you now one other application in there in the notes, just a few lines. And we'll see we see them appear again at the very end of the course when we talk about graphical models. So you're very likely to come across them. And so once you know these kind of facts, these are the kind of things that you need. Now, what was quite important in this thing was one other element, and this was what I had called the link function. And so in general, what we mean by this, it's this relationship between this parameter eta here that appears in here, and a natural parameter that, of course, that often you would use to specify the distribution, and that's just this mean function here. So we have seen this in particular for the one-dimensional case, like say the Bernoulli or the Poisson one. So there the natural parameter was exactly the mean there. In the Gaussian we had used really the mean and the variance, but this vector here was the first and the second moment, but we could have just taken also this parameterization here. So let me just call this mu here for the mean. These are all vectors. And so the interesting part, and this was called this link function, was this relationship between the two, right? So you're giving me a parameter here. So there's some fixed vector, x squared, whatever. And then you're giving me a particular vector eta. and assuming that you can then find a normalization constant that gives you a distribution. Under this distribution, you will get a certain mean. Okay, so mean here means the mean of that particular sufficient statistic. Okay, and so so that's clear in principle for any eta. Assuming that eta is something that gives you a valid distribution, there's a mean. But we have seen that sometimes also it's interesting to see that if you have a certain mean, that you might be able to go back and see if there's a parameter eta. Okay, and so it turns out, and we didn't do this, and it turns out that under fairly mild condition, you can basically go back and forth between them. Okay, so as long as there's any distribution that has any distribution has some particular mean, okay, then there will be an exponential one that has that mean, and so there will be such a parameter here. And so in principle, you can go back and forth between them. They're both equivalent ways of describing them. And for simple ones like the Gaussian, Bernoulli, and so on, there's an easy way to do. We can, and there are tables for simple ones. But there are distributions where you don't just have one or two parameters. You might have hundreds of parameters or thousands. When we get to graphical models, there might be hundreds or thousands of parameters that you have. And then in cases like this, in particular, if we then not over the continuous but maybe discrete, it might just be basically this exists and is well defined, but it might not be possible to simply compute this. Okay, so we have seen that for simple cases, we did two applications. Right? Or we talked about one application. This was when we talked about generalized linear models, which was basically the equivalent of logistic regression, but for more general wise. And I wrote you another one in there, which is just even something simpler, parameter estimation. And I'll let you read it. It's something even much simpler than the second one. And so if this function here, if these are simple and you have this link function here explicitly or can easily compute it, then because of the convexity that we have here, we've seen that this leads to something computationally efficient, right? Like in the logistic regression, this leads to some, system of equation that we can, cannot maybe explicitly like find something like a least square formula, but at least it's convex and computational. You can just run some gradient descent, and all the quantities in there are simply computable. But even though you have the convexity, if you have models where you have many, many parameters, then even just, for example, the normalization constant that you have here, which is like an integral over this domain, let's assume it's continuous, this might be a sum, it's discrete, might be a sum over hundreds of variables, even everyone taking on 0 and 1. So this would be an exponential sum. Okay, so sometimes you cannot do it, even though it might be convex, it might simply be computational very difficult. So take-home messages, exponential families have this form, they have some nice properties, and they appear pretty much anywhere. When you talk about machine learning, you will come across them quite often. Okay, end of the story. So now what we want to talk about now is a second way of doing classification. And we have already mentioned it, but today we want to analyze it. And you will, after that, see two other ways then to do classifier. So next week, you'll talk about support vector machines. And so that's another way of doing classification or linear classification. And later on, we'll then talk about things like neural nets. And also with neural nets, you can do classification. So you'll have then at that point 4 different ways of how you can do classification and to some degree also regression. And that kind of covers some of the main techniques. There's some other ones like decision trees and so on. But these are kind of the major ways of doing it. And there's not one that necessarily uniformly is better than anything else. Depends a lot on the case. So what is the nearest neighbor classifier? Well, we already shortly mentioned it. You think, again, you have some data. And so this data will be some xn and yn. And this kind of classifier really just works, and we'll see today why, if we're talking about very low dimensional data. So the xn is maybe in 2 dimensions or in 3 dimensions. Okay, if it's high dimension, anyway, this won't work. So we don't really lose much by drawing pictures, because that's really when things work. So you have you have your input. And so this is in some r to the d. For the most part today, when we do analysis, we'll assume that it's in 0, 1 to the d, a unit box. Okay? And then this yn, again, so let's assume it just takes on the labels 0 and 1. But you can also, think about it if it's not just classification, but regression, and then this simply might be some value y. Okay, and so now we have, if we think of the classification scheme, then we'll have points, and if I use 2 colors to denote these points, then there will be the points that maybe whatever correspond to, maybe this corresponds to 1, and maybe this corresponds to 0. Okay, and they will be somehow spatially distributed, and I don't know how this will be, right? And so this will be distribution. This can be quite complicated, and so that's the advantage. That there doesn't have to be any obvious structure in here. And so now the whole idea was the following, that if I get a new point, so I get a point now here, so this is a new x, which is not in my data set, that then I'll have a function, and this function, it's called neighborhood, NBH. It depends on the set of points that I've given, and it will return me k points, where k is an integer. So k could be 1 up to something. And so this is a set of k nearest points to, and the input is to x. Okay, so I give it a point x, and it returns to me the k nearest points to x, and nearest, okay, so this is nearest point in x in, out of the set st, right? So it gives me this. So, and, let's assume I had such a function. There might be a question, how do I computationally efficient do it? Because I might not want to just go over all the points every time, but there are there are efficient ways of finding such things. So now if I did classification, right? So then what I could do is I could simply look at my classifier. So maybe call it y hat of x, right? I could simply look at this set, the neighborhood. So I could look at the set of the yn, where the xn is in this neighborhood. So I look at all the labels y, where the x is one of these close guys, right? And then, for example, if this is just a 0, 1 function, I can just look at the majority. Right? So for example, if in this set there's 3 times the label 1 and 1 times the label 0, then I should pick 1. That's my return function, right? That's my guess, right? And so of course there, if I want to do classification, it might be good to pick maybe k odd so that I always have a majority. And today, of course, we'll just talk about when k is equal to 1, in which case it's particularly simple. All I do is I'll figure out which one is the closest point. So perhaps it's this point here. Okay, so that's my neighborhood of size, neighborhood of size 1. Let's assume that's the closest point. This point has a label, and I'm simply returning that label, right? And if it wasn't classification, but I did regression, well, I could do something simple or similar, right? So if I did regression, and I get some point x, right? And so that's based, of course, on this. Then what could I do? I could take simply the average, right? So I go over all n such that xn is again in this neighborhood st and k, so of x. So all the points, the k closest points to x. For each of these points, I get an output yn. I have k of those, and I take the average. And that could be, a possible prediction that I make. Clear? Right? So that's not very complicated. Yes, please.
It's too small. What does it say there? Like why happens?
So this, it's just neighborhood, okay? NBH is neighborhood, okay? I don't want to write it out every time. It's the neighborhood. It's the neighborhood. Oh, the majority. Okay, majority. Okay. So I mean, in principle, the function is right. That's not very complicated. So our aim today will be to prove what I told you last time, and essentially there are two messages they want to get across. Number one, if you're in low dimension and have lots of data, then that's a very good rule. And very good will mean that we can prove that it's a probability of error. So we talk about the classification. So we'll see that the classification error is at most at factor 2 larger than for the best thing that we could be doing. And the best thing here would require that we even know what is the relationship, probabilistic relationship between x and y. So if we knew the probability that we see a certain label y for every x, right, because in general there will be some noise, then we could do the what's called the maximum posteriori estimator. So that has the minimum probability of error, and we'll do at most a factor 2 worse than that. That's good news. The bad news is that that's true as long as the dimension is fixed and n goes to infinity. The bad news is that if let's say n is fixed or grows slowly, less than exponential, and d increases, we'll do arbitrarily bad. Okay, so this is not something that you should use if you're in high dimension, but if you're something very small dimension, it's reasonable. Now, before we go there, let's just again remind ourselves a little bit. So let's just look at, for example, the bias variance trade-off. So just that we see, because this looks very different than what we have done. So let's just by picture, just see what we should expect. So if this is the error here, then we have here complexity of the model, right? Complexity. So complexity is large, complexity is small. So what is the complexity? You know, how do we, the only thing we have here is the parameter is the k, right? If we're taking many k, then we're kind of averaging over a neighborhood. If we take k to be 1, we just take the closest point. So how does k relate to complexity? What is what is the most complex model? K is 1, right? So the claim is that the most complex one I can do it if k is 1, and this one is k large, right? Imagine that k is of the order of n, my data size, then I'll just always return the same value, right? Then I'll just average it out, everything, it's very smooth, right? So this might be a terrible predictor, but I have 0 variance, right? No matter what I give you, I always give you the same, okay? Whatever the input is. So this means we should expect, so there will be several things, right? So this will be kind of, let's say, the optimum world, the base 1, and we'll talk about it. This will just be given by the noise that I add, right? So if the y is not predicted by the x, but the y is x plus some, there's some variation in there, then I'll never be able to do better than this noise that's inherent. And then I'll get some curve, let's say maybe something like this. So this will be the test error. And then I will get some other curve, maybe something like this. This will be the train error. So what will be the train error? So just to get our bearing, what is the train error if k is equal to 1? Loud.
Like it's always 0.
Because, when k is 1, I mean, the only examples that I get are from the set itself. What will I get back? Well, if k is 1, I get that same sample back, and I compare it to myself. So I get perfect, right? So that's not very surprising, but it's also not very useful, right? And of course, if I would average out, right, then what I will predict will be more and more larger averages. So, in general, you would assume it gets worse, right? And so here, in this case, we have again, for the actual error, we have again, a similar trade-off as we always have for, if k is too complex, okay, then we might overfit. We just, we predict something, maybe, that's just too, might not just be a very good fit anymore. And if k is very large, then we'll just predict an average, and that's not going to be relevant either. Okay, so that's just the same as we have always. So that's not particularly interesting. So now let's us convince first, on a casual way, of why D large is bad. Okay, so why is it difficult? It's also called the curse of dimensionality. Why is it difficult to do such prediction when D is large? And last time I tried to do this packing argument. Okay, so let me give you now something that slightly different argument. So just imagine we have the unit cube. Okay, so we're looking at 0, 1 to the D. And we then think of D being larger and larger. Okay, and let's assume that X is uniformly distributed in 0, 1. Okay, so later on we will not assume that we know what the distribution is, but right now, just to see what happens with the scaling, we assume that my data in there is uniformly distributed, right? And so now, let me do the following. Let me take a unit box, not a unit box, a box of side length here, R. So this will be R, right? So this means this box will have R, so the volume of this box will be R to the D, and the volume of the big box is, of course, 1, right? Clear? So now let's assume I did this K nearest neighbor thing or something, and so then maybe I want a certain fraction or something to be of the data to be in such a box, right? Because so I imagine that I'll pick the box somewhere, right? And maybe I pick it around the center of the thing, or something. And now I hope that within that box I have some data, right? I hope that that's the equivalent. Last time we looked at spheres. Now I'm just looking at a box. It's slightly easier to compute. So I just hope that there's some data in there, right? And so the question is basically how much data do I expect to find in there, right? So what's the fraction that I have in here, right? And so you can see here, right? So that if you want that to be some certain alpha, let's assume you want to do K nearest neighbor, where K behaves like some fraction of the data, okay? 0.0001 of the data, some fraction I want to have in there, right? So you can see, of course, in here that the R here, right? So this is maybe whatever, 0.01, something like this, okay? I want that to be a certain fraction. So you can see, of course, that the R will be this whatever fraction you want over 1 to the D. Okay, and very, very quickly, when D goes up, this will go to 1. Okay, which means you basically, in order to capture a fraction of the data in there, you have to essentially look at over something that's more or less the box, right? And a computation that's essentially the same, but maybe just slightly thinking differently, is the following. So let's assume I have again exactly the same setup. What is the size of a box so that with probability a half, there is at least one point in there. Right, because in the previous computation you might say, well, why do I want a fraction of the points to be in there? But clearly, if we want to do a prediction, and even if k is 1, we would like that there's at least 1 point in some neighborhood, and the question is, how big do I have to choose the neighborhood that there's a decent chance that I have at least 1 point in there, right? And decent chance just means here half. Okay, the half is just some arbitrarily constant here, right? So I'll pick the box. And so then if that happens, then at least within that distance, right, of this box, I find a neighbor, right? So So if I have one point, so if I take one random sample, and I pick it uniformly at random, so I pick the box somewhere here, doesn't matter as long as it's inside. I fix the box here, and now I throw randomly a sample in here. What's the chance that the sample does not land in that box? Okay, so sample is not in the box. Right, so it's when it's everywhere except in this volume, right? And the total volume everywhere is 1, and the volume of this small little box is r to the d, right? So that's the probability that it's not in there. Now, let's assume I don't have now just one data point in there, but of course my sample has size n. So what's the chance that none of them is in there? Right, so I just do this now to the n. And let's assume I want this to be a half, okay? Right, so I set that to be a half. So that's the chance that this would be the kind of, so I'm looking for the relationship between R and D, such that the chance that none of the points is in there, or that a point in there is exactly a half, okay? Or at least a point in there is exactly a half. Okay, so now this means I take 1 over d, so a half over 1 over n, and then this is a half here, 1 minus, and I get here r is equal to 1 over d. Right, so that's how large the box would have to be, so that I have at least some decent chance that I see something, right? And so now you can plug in numbers. I guess if in the notes is something given, if n is 500, which is a decent thing, and d is 10, which is not an enormous large space, right? Then the r I think is 0.52 or something. So if n is 500, d is 10, which is quite small, then the r turns out to be 0.52. Right? So again, you need, so this notion of a close neighbor that's very familiar to us in, let's say, 1 or 2 dimensions, right? You all have close neighbors, and then there are people that are much further apart. That notion is not, very meaningful if we're talking about high dimensions, because even your nearest neighbor, right, is about, in every dimension is about half the box length away, right? So it's very far away. So this notion of what's closer, basically you have to imagine that in high dimension there's no one, okay? You feel all alone, okay? And then suddenly there's everyone, okay? So then if that's happening, then it's not very meaningful to ask that first person that you meet, because that's essentially a random person, okay? Doesn't have much connection anymore to what you are interested in. Make sense? Now, our aim will now be to analyze this. And so in order to do this, we'll have to make some assumptions to set things up, okay? And as always, of course, this assumption may or may not be true, but it will give us some idea. So the assumption will be that so we'll look at the classification case, and the assumption will be that the x comes from, again, this box, but there's an unknown distribution. We don't assume right now that it's uniform, okay? So unknown, so we have some underlying distribution x and y, but it's unknown. We don't assume that the x are chosen uniformly, and we don't know what the relations, if I give you a certain x, I don't know what the probability of the label is y, okay? There will be some relationship. So this is unknown here. Then the y, 0, 1. And then we have our test set, which is, of course, as always, the xn and yn. Okay, so we have this. And we assume these are just some IID labels, IID samples. Now, clearly, in order for nearest neighbor to make sense, we have to assume that x gives us some information about y, right? The only thing that I see later on is x. And so if x contains no information about y, if thereif no relationship in here, right? No spatial relationship about the y, or saying, let me put this in a different way. If I know an x and I know a close by x, if I can't at all conclude on somehow what this means about the y, then I don't think that the samples that I have that will help me. Okay, and so the way to formalize is that we make an assumption. It's what's, so the assumption is of kind of some Lipschitz assumption. I'll tell you what this means. And so let me define the following. Eta of y. So, eta of x. Let me define the following. There is an underlying distribution. And for the underlying distribution, if you tell me what the x is, and I know what the distribution is, then you have to imagine that now there's a certain probability that I get either y is equal to 0 or 1. Okay? So if it wasn't noisy at all, then this function would be deterministic. So for every time I tell you an x, you should always see the same label y. But since there might be noise in the system, it might simply be that with high probability, I will, for a certain x, I will either see the label y as being to 1 or I see the label y is equal to 0. Okay? In the noiseless case, this would be completely deterministic, right? For every x, there's either a 0 or 1, and every time I see the x, I would see the same label. But in general, there might be some noise in there. Okay, so I might not always see the same label. Good? And so just so that we have a little bit less to write, we'll write eta of x. Eta has nothing to do with any other eta we might have ever used. Okay? So, good. So now, what I would like is, right, so remember, I get maybe a new sample here. I have some other samples around, right? And so I find maybe the closest one. And then my idea now will be, we look at the of k is equal to 1 case. And so our idea will be that I simply return the label of this guy, right? And so what we kind of need is that if things are close, that this probability doesn't change too much, right? So let's assume I'm at a certain x, and 99% of the time I get 1 back, and now I'm moving just a little bit away from the x, then I better get most of the time still 1 back, right? If there was absolutely no relationship between the two, then how could I hope that this past sample tells me something? So what we want is the following. We want that eta of x, let's say 1, minus eta of x, let's say 2. We want that difference in the probability. So we want that this probability is smooth, doesn't change too much locally. And so one way to do it is to say that this is less than some constant. Okay, so this is what's called the Lipschitz constant. And I simply say this simply depends on the distance. Okay, so I just take the Euclidean distance here. So if things are very close by, then these probabilities are essentially the same. Clear? And this constant is just some constant that's part of our assumption. Okay, so it's a constant, and that's part of our assumption. Okay, hopefully this constant is small, so that indeed this makes sense. The important thing is that we all, this might not be the only assumption that you can do to make it meaningful, but I hope you all then, it's clear to everyone that we need some assumption, right? That close by points help me to predict. Right? Imagine, for example, if there's no noise in there, so that this function is completely deterministic, right? Then you basically have areas, right, in which everything will be 1 and areas in everything will be 0, right? And so you want these areas to have kind of, that they're well-defined areas, so that you're somewhere in between. If you now go a little bit close by, that you're likely still going to be in the same area where it's either 0 and 1. That's what you want, and that's just a probabilistic version. So now what would happen? So what is the optimum rule? Assuming that P, or this that this eta here of x is known. So let me call this the rule F star. So if I get an x, and I knew what this distribution is, I knew what the chance is that I get either 0 or 1, right? because for every x, this eta tells me, whatever, you know, it's the chance, then what would be the optimum rule? What should I guess?
It's greater than It's greater than half meter.
Right? So this is the chance that it's 1. If this probability is larger than a half, okay, so if this eta of x is bigger, and I can split it where I put the half, if this is bigger than a half, then the chance, given that I have the x, to see the y labeled to be 1 is more than a half. Okay, there's a bigger chance to see a half than a 0, and hence I should go to there, right? And then, you know, that's the optimum rule. So you can say base rule, or map rule. And we talked several times already that that's the best we can do, that has the smallest probability of error. And what is the probability of error? So if I denote this probability of error for a particular x by L, just my loss function, that's my probability that I make a mistake, then what is the probability? So I get 100 times I get x, and every time I do according to this rule. What is my probability of error? What's the chance that I'm wrong? 1? That's pessimistic. Sorry?
1 minus 7. Oh no.
Oh no, oh no. So let's assume it's 90% of the time it turns out to be 1, okay? So you guess 1. How often are you wrong? 1 minus, okay? So you're going to be wrong 1 minus time of the time, okay? So this means that this is exactly the min of the eta of x and 1 minus eta of x, right? Why? If the eta of x is larger than a half, right, then you're going to guess it's 1, and you're going to be wrong 1 minus eta of x times, right? Because that's the probability to get actually a 0. If the eta of x is less than a half, you're going to guess it's 0, right? And you're going to be wrong eta of x times, okay? You're always the smaller of the two probability you're going to be wrong. Make sense? Can we let that sink in? Okay, good. So, okay, so that's my probability of error. And so now, of course, you know, I can still do now the expected value, right, over all the x element of D. And so I would have here the expected value x element of D, right? So that's my, that will be the kind of the standard error. And later on I might write this. I might write this whole thing just as a shorthand as the loss of this function. Okay, if I have no argument in there, then that's just the loss of the optimum function. That will be like this. So this will be our golden measure. Of course, in general, we can't compute it because we don't know what eta of x is, right? So we won't be able to compute. I can't give you a specific value. But what we will manage is we will relate our task or our error to that task or to that error. Okay, and we'll see that compared to that error, it's at most twice as large plus something else. And this something else will have to do with the number of samples versus the dimensionality. That will be the idea. Okay? Good. So, so now let's continue, right? Okay, so let's see. So we have the following claim. You know, our function, I guess I didn't write this down. Maybe I should still write it down here. So, you know, we take, when I write f as t of x, right? Then, so if I write this will be the one, this is the nearest neighborhood rule, right? And so this will simply be that return a label of this neighborhood st1x. Okay, so it means I give you a point x, You find the closest point in the set ST. That point has a label. That's the label you return. Okay, and so when I write this FST of X, that's the rule there. Make sense? So now, of course, this, and this, of course, has also an error, right? So there will be, there will be an underlying error for that. And so the claim is that this has the following. If I'm taking, so there are several kind of things that are random in here. If I'm looking at this rule, and I'm looking at its average loss. So what is the average loss? The average loss is that I predict something, but the actual label that corresponds to it is not that label, right? Right? Yes?
The neighborhood function, we have a 1, a k, or the rest?
So this is a 1 here. So this is just I'll analyze everything for k is 1. So I write everywhere 1, and perhaps I might even forget, okay? But everything is 1 here, neighborhood. Okay, you can do something similar for a higher dimension. It will not really, if k is any other integer, it will not change the dramatic scaling, okay? Constants and so on will scale. So, okay, so now, this is now the loss. So there are two things that are random. It's the set that I get, right? So we better average out over this. Sometimes I might be luckier than other times. And it's of course also the point at which I'm being cured. Right? So there's a certain point which I ask to be returned. And so the claim is that this error is no more than 2 times the optimum error. So this I called L of F star. So this is the optimum error that I could hope for. And then I get an extra term. And so this extra term has the form C times the expected value of the x minus, neighborhood st1 of x. So this is the difference between the random point x that I have and the closest point there is. Okay, so it's a geometric term. And let me first write down, and then we'll take a break, and afterwards we'll then discuss all this thing. And this thing here itself is smaller equal than this plus, and I get something d square root of d. What do I get? I get okay, so I get this particular form.